It's wonderful to be working on quantum computing with this team, and I'll talk a little bit more about that. But just to get going on the technology, Arthur C. Clarke, the science fiction author, once said, "Any sufficiently advanced technology is indistinguishable from magic." And when you look at a quantum computing chandelier, the top of that chandelier, it's all about getting the temperature down. That's what all that golden glass is for. So it's normal temperature at the top. It's 4 degrees C at the bottom, 4 degrees K, sorry, 4 degrees above absolute zero at the bottom platter. And at the very bottom, where the quantum qubits are, it's a few millikelvins, thousandths of a degree Kelvin above absolute zero, colder than space. So that's all pretty magical. And we're going to get to work with some of you, I believe, in being one of the early applications of quantum computing technology to real world problems. So it's a pretty exciting trip we're launching on. I have 10 slides here that I'll share with you, and I won't read off the titles now because we're going to go into the details. The purpose of what I'm sharing is not at all a deep dive. It's just to orient you so you understand the news from quantum computing that you're seeing now and that you'll be seeing in the years ahead as we get closer to the things delivering real world results. And finally, a big thanks to One Market Data for hosting us. Everything I've experienced in working with the team there has been amazing. First of all, there's a dummies book, which I co-authored. My co-author is Worley, who's head of Strangeworks, which is one of the most important companies in this new field. And I worked on the book with him. I'm a professional author. I've had books out for decades and sold a total of 1 million copies over that time, largely in the Dummies series. And Quantum Computing for Dummies is my latest and also the most fun. Just enthralling stuff. And I'm very happy to be now working on a company bringing this to the world. The core of quantum computing is the uncertainty principle. So this is a very amateurish explanation, and one of our friends, Matt, who Tom introduced on that slide, did explain to me that a number of quantum physicists are in the audience. So if I have a little anxiety here, that's why. However, the layperson's explanation is that the uncertainty principle says you can't both know where a quantum particle is and its speed and direction at the same time. If you hone in on one, you get increasing uncertainty on the other. And, there's a practical example. If you want to know where a photon is, you have to put a detector out and stop it. Well, okay, so the moment it hits the detector, you know where it is, but you've changed its speed and direction because you stopped it, right? So all of that uncertainty is where the possibilities go in, that Tom will show you in computer code for quantum computing. So really exciting. I won't explain the Schrodinger's cat experiment. Sorry, you put all this stuff in a box, the radioactivity decays, the hammer goes down, the cat either lives or dies, but you don't know until you open the box. And there's a philosophical statement that the cat is both alive and dead at the same time until you open the box, which is not strictly true, but it does capture what's happening at the quantum level in an example we can all understand. Then you take these mysterious qubits and over there on the side, you entangle them, which is a kind of a mysterious connection between these quantum particles. And Einstein called Einstein said about uncertainty that God does not play dice with the universe. He called entanglement spooky action at a distance. He had questions. So this slide is from the fifth Solvay conference. It was between 1900 and 1930 that quantum mechanics was first laid out. Niels Bohr is over to our right in the middle seated. And then there's a book here, Quantum Drama, about the back and forth between them. And this is finally being resolved in the favor of Bohr in many ways, not to throw stones at Einstein. His work was fundamental to quantum mechanics and to so much else in our modern world. But he did bring up some great questions. The Nobel Prize in 2023 was awarded to 3 gentlemen who proved entanglement to successive degrees of certainty over a number of decades. So this is real stuff. The Nobel Prize just went out in 2023 for it. Quantum computing does work. This is from the book the Dummies book, and these are some of the key players. I did not mean to put up a stock of investable quantum computing companies, but I accidentally did that. All I was trying to show in the book was not how to bet your stocks, but I was trying to show which qubit technologies different players are using. And I won't go into this in detail, but when you're using a new technology, eventually there are probably going to be one or two technologies that carry the load in quantum computing. Right now, there are at least five, and all of these players are spread among them. So all of these investments you hear about and all of these stocks that are going up and down, probably only half a dozen of these companies will still be doing this in 5 or 7 years. At least that's the way it has usually worked in the past, right? We don't know. It's uncertain what's going to happen. However, there's a lot going on, and the future probably doesn't have this many active leading players in it. It's still very much in the early stages. I followed the early days of microcomputers very closely because I've been around long enough that I got to do that. And that was early in my career. And this just demonstrates that it's still somewhat of a science project, making these things work. I'll just mention that introduced a chip, a MUX DMUX chip called Pandotree that operates at the millikelvin level, which I will explain to anyone who asks me at some point at great length. You might have to buy me something to drink or eat while I'm going on about it. I won't now, but this is just to get your guys' heads around the fact that this is not in strong production at this time. However, this technology is expected to break RSA someday. And let me spend a minute on this slide because it explains where finance fits in the realm of applications for quantum computing. The two blue lines in the lower left of the slide show IBM's Eagle quantum processor from a 2023 result in which they delivered an experiment in the computer showing how up to 17 magnetic fields interact. The classical computer could only keep up with the IBM delivering the same results up to 9 magnetic fields, and only the quantum computer could do fields, 10 fields, 11 fields, up through 17. Those results cannot be verified on a classical computer because it would take too long. So that actually is our first solid real world result, which only happened a couple of years ago. In my point of view, other people say other results are real too. So there's disagreement on this. But now the time dimension for this graph goes up and to the right. It's not strictly left to right because the vertical axis is the number of qubits being used, and the horizontal axis is the number of logical operations, the number of steps in the program, which are called gates in quantum computing. And you see that arrow going through. So factoring is low-level factoring. It's easy factoring, better than we have now. Then next on that arrow, across that arrow, three different instances of derivative pricing, along with first stage quantum chemistry and quantum dynamics. So you see that we'll probably get some early results from the physics world first, like those magnetic fields, that hopefully will have some practical applications. We might see a better battery, for instance. But then we get into being able to run finance, and in the simpler versions of quantum chemistry, hopefully get us a couple of drugs, that help some people at that point. And then Tom and I will be working together. Tom will be doing the hard work, but I'll be getting the word out to get some results to you guys where we can actually do probably first historical analysis of options and similar pricing functions, and then increasingly advanced and increasingly timely results as quantum computing gets better and better. But you see that RSA 2048 and so on is even after some pretty advanced quantum chemistry in terms of difficulty. So that won't happen everything everywhere all at once. This will be spread out over a number of years. It may, for instance, be 10 years between early finance results and serious cryptography breaking. Programming quantum is a new world. The gates are different. They're not the ones that you're familiar with from classical computing. These tables are also from the book, so it puts it in some kind of context. And only some algorithms can be worked over into being effective on a quantum computer. There are different algorithms at that point, but to do the same things. And the ones that are effective today are arranged in families, or theoretically effective today, because the hardware is not ready yet to run them really well. And so I think the book can help you if you're interested in understanding what works on a quantum computer and why some other things don't work, and how they relate to each other in terms of power and so on. The great thing about finance for quantum computing is that even very small advantages in performance have a big real world effect. Best thing for finance is that the best thing that quantum computers can do, besides chemistry and physics, is to find one correct answer out of many, many possible answers. You know, when you get a combinatorial explosion of X number of stocks and Y number of times that you could trade it and Z number of market conditions, and you end up with these immense numbers. And a quantum computer can actually find the answer to that. It does not calculate it in the same way a classical computer does. The answers somewhat, you get all the answers to live together at once, and then the right one kind of falls out, is the analogy that I'll use for it. But Tom will be showing you, actual code of working through this. A couple more things. Government and industry are working very hard. Now, these are the above the line investments from governments that total about $40 billion. There are also below the line investments. Some of the early work on quantum computing was funded in secret by the National Security Agency. We know this because a WikiLeaks type effort found the paperwork and published it. So this is not all the government spending that's going on, but it's the part that is shared with us. And then industry is working on quantum computing, as you know, and as you see in the news all the time. And so are we. So Tom and I went to a quantum computing conference together in December, and I started talking to Scott Aronson, who's one of the very leading lights in quantum computing, in the lunch line. Tom came along, and they had a long and animated conversation, and it was a real pleasure. And I think that Scott might have been happy to see some workers in the field, looking to actually apply this in the real world, and somewhat not caring about some of the industry arguments that are going on, right? Just interested in getting some really cool things to happen for people who are aggressive and interested and want to make things happen. So that was a lot of fun. And back to Tom.
All right, Floyd, thanks a lot. Great presentation.